Welcome to E-Padasala lecture series in computer science. In this particular module, we are going to discuss more problems that are coming under the category of transform and conquer design paradigm. The objectives of this particular module is to explain how the matrix decomposition can be performed. So, for this we are going to use the Gaussian elimination method, and we are going to discuss about a procedure called the Kraut procedure. Using this we can perform the matrix decomposition, and as I said earlier in the last module, the main objective is to solve problems that involve matrices like matrix inverse and determinant. So, the objective of this particular module is to develop algorithm that uses transform and conquer procedure to do the task of matrix inverse and matrix determinant. So, last module we discussed about the transform and conquer strategy. So, probably you can recollect this is a two stage solutions. So, in stage 1 we are trying to transform a problem into another problem that is more amenable for solutions. So, last module we discussed about how to transform a problem that involves multiplication of two numbers in Roman system to numbers of the Arabic system, and we have seen that how after performing the multiplication it is transformed to the original solutions. And we also discussed about how to solve the problem of convolution. So, you can see that in the last module we used the FFT to transform problem from the spatial domain to the frequency domain, and in frequency domain the convolution problem is reduced to plain multiplication, and after performing the multiplication we used the inverse FFT to get back the convolution of the original signals in spatial domain. We also discussed about how to transform problems of what is a LCM to GCD finding. So, we also said that the various variants are the instance simplification, representation change, and the problem reduction, and we have started the discussion of the instance simplification only, where we discussed about the Gaussian elimination procedure. So, the important aspect of solving the matrix inverse and matrix determinant is the LU decomposition procedure. So, LU decomposition is another method of solving the simultaneous linear equations, and once we have a non-singular matrix A, then we can decompose the matrix A to LU. So, the logic is very simple. By multiplying L into U matrices, we will get back the matrix A. In other words, the matrix A can be represented as the product of two matrices, that is the lower and upper matrices. So, L is going to be the lower triangular matrix and U is going to be the upper triangular matrices. So, what is the advantage of this? The advantage is very simple. Given n linear equations with n unknowns, we have seen that we can represent that by means of the matrix notation as Ax equal to B, where x is going to be the unknowns that we have to determine. So, now what we are trying to do is we are trying to decompose this A to two matrices L as well as U. So, now you substitute this back into this equation. Now, this becomes LUX equal to B. So, first you assume that y equal to Ux. So, that means now it will become Ly equal to B. So, now we can solve for the unknowns y, and once you have the y, you can substitute that what is into the equation u x equal to y, where we know u, we know y. So, now we can find the unknowns x. So, this is the advantage of this method. You can see how beautifully the concept of transform and conquer works in this particular case, where we transform one problem to another problem that is amenable for solutions, then we solve that, and the solution of that represents the solution of the original problem. So, these are the essential properties of LU decomposition. So, not all matrices will have LU or factorization way. So, it is only for non-singular matrices it is possible. Sometimes we may have to swap the rows or columns to make LU decomposition possible, and LU decomposition is guaranteed if its leading sub matrices have non-zero determinants. These are some of the properties. So, now we will take the same problem that we discussed as part of the last module, and we can use that discussion for creating the matrices L as well as U. So, you can see that we are taking the same problem that we discussed in the last module, 3 equations with 3 unknowns. So, you can see that the first step of the Gaussian elimination procedure is to create a augmented matrix. So, you can see that the vector B is augmented into the matrix A to get a augmented matrix like this. Then we have seen that we have to keep 3 as the pivot, and we have to eliminate the corresponding coefficients in the other equations, and this is done by means of the elementary operations. So, you can see that using the transformations we have eliminated 6 as well as 1 of the third equations. Now, we can keep 2 as the pivotal element and we can eliminate 2 by 3 in the third equations. Now, you can see that we have a reduced what is a system of equations using which we can find the unknowns. So, now from this we can find the matrices L as well as U. So, U is going to be the same as the coefficient matrix at the end of the forward elimination step. So, that means whatever we have in the end is going to be what you say the part of the matrix U, and L is obtained by using the values of the various multipliers that are used to eliminate the corresponding coefficients of the other equations. So, what is the multiplier? So, you can see that the multipliers that we use to eliminate 6 and 1 of the other equations are 2 and 1 by 3, and similarly you can see that we have used a multiplier of 1 by 3 to eliminate 2 by 3. So, now you can see that by substituting the multipliers and by keeping all the diagonal elements as 1, we are getting a matrix of L. And what is U? So, U is going to be the same matrix that we obtained in the last step of the forward elimination procedure. So, now you can see that the matrix U is going to be the matrix where the lower part are going to be the 0 and the upper parts are going to be what you say the numbers that we have as the last step of the things. So, now the logic is very simple. Now, we have decomposed the matrix A into what you say LU. So, now as we discussed earlier, now we are going to replace Ax equal to B into the procedure of Lux equal to B. So, now we can set Ly equal to B. So, now this is the matrix L which we obtained in the previous step. So, now you can see that by substituting this it becomes something like we have to find y1, y2, y3. So, you can see that the values of y1 and y2 we are finding and y3 we are finding. So, once we have this, then we can substitute that into the old equation of ux equal to y, where we know the value of y, we know the value of u. So, now we can find the unknowns, that is going to be x1, x2 and x3. So, now you can see that the values are 2, 4, 1, which are going to be exactly similar to the value that we obtain as part of the Gaussian elimination procedure. So, now you can see that the results are going to be the same, but one extra thing is instead of solving Ax equal to B, now we are using the transform and conquer paradigm of replacing A by Lu. So, we are trying to solve the problem of Lu x equal to y. So, we can generalize this as a recursive procedure. This is the procedure that uses the Gaussian elimination technique. So, you can see that we use the pivotal value A11, and by keeping this pivotal value A11, we are going to update A21 by dividing that by means of the pivot value, and once we have that what you say the value of A22 is going to be recursively computed using this particular procedure. So, you can see that this is recursively applied to what you say the given matrix to get the resultant. Let us try to apply that procedure to the numerical problem, so that we can have a complete understanding of how this really works. So, now we are given the matrix A. So, now the job that is given is we have to perform the LU decomposition for this. So, now this is the matrix which I am going to take. So, now you can see exactly what is being done here. Now, 3 is going to be the pivotal element. So, that means you can see which is illustrated in the second column of the table, where we can see that the A11 is chosen as a initial pivot, and the entire column is divided by 3. So, that means you can see that 6 is getting divided by 3 to give 2, and 1 is divided by 3 to give 1 by 3. So, that means you can see the transformation that is happening. So, keep the pivotal element and try to divide the entire column by means of that particular element. So, you can see exactly what is happening on the third column. Third column, now this A22 is going to be updated. So, you can see that the capital A22 represents the matrix that is 4 1 1, and now you can see exactly how this recursive transformation is taking place. Now, this is equal to what you say, you can say 4 1 1 minus 2 1 by 3, which we are getting in the previous step, multiplied by your 1 1 1. So, that means 1 1 1 you can see is present in the second quadrant. So, now you can see that by doing this particular operations, the values are going to be changed, and you can see that we are getting a matrix that is what you say 3 1 1, and we are getting 2 2 minus 1, 1 by 3, 2 by 3 and 2 by 3. Now, you can see very well that the recursive procedure is again invoked now. So, now 2 is taken as the pivot element. Now, recollect what we did in the previous step, divide the entire column by means of this pivotal element. So, that means you can see that we have only one element as part of that column. Now, that is what is divided with 2 to give 1 by 3. Now, A22 is going to be only one element, that is going to be 2 by 3. So, now you can see that the updation procedure is 2 by 3 minus 1 by 3 multiplied by only one element is in the second quadrant, that is going to be minus 1. So, after performing all these operations, we are getting 1. So, now you can see that the final matrix is going to be given like this. So, once we have this matrix, fine, we can generate L and U like this. For the matrix L, the diagonal elements are going to be 1s, and all the upper elements are going to be 0, and you can see that the rest of the elements will go as the element of the matrix L. And for matrix U, you can see that it is the value of all the upper elements, and all the lower diagonal elements are going to be 0. So, now this is going to be the matrix L as well as U. So, now we can verify this whether this is right or not by performing the multiplications L as well as U. So, you should get back the original matrix A, then only we can conclude that the procedure is going to be right. So, this procedure is a recursive way of applying the Gaussian elimination to find matrices L as well as U. LUP decomposition is a slightly advanced algorithm of LU. Suppose as I said earlier in the last module, suppose if one of the elements happens to be 0 or a least element, then in the elementary operation, if you substitute that, we will get larger integers. In that case, we may have problems. So, in that case, we may have to swap the equations to apply the Gaussian procedures. So, in LUP, that is also added as a matrix operations. So, P is going to be the permutation matrix, so whose values are going to be 1s and 0s only. So, that means now the physical location of the equation is not touched at all, but the logical position is being controlled by the values of the matrix P. So, now you can see that the logic is very simple. We are simply adding P as part of LU, and rest of the things remains the same. This is the informal algorithm using which this LUP decomposition is performed. This is the third procedure, which is very popular. This is called the Kraut's method of LU decomposition. So, here we are using a slightly different logic than Gaussian elimination. So, you can see that the matrix A is decomposed into two matrices L and U, where L matrix is having a structure like this, where the diagonal elements are going to be 1, and these are the lower elements, and the upper elements of this matrix L are going to be 0. Similarly, in the matrix U, the lower matrix is composed of element 0, and upper elements are composed of elements like U11, U12 and U13. Now, in Kraut procedure, we have to find the value of these things by direct substitutions. So, by means of that we can find that. So, now you can see that how these values are obtained. So, L11 is what this value is, this is L22, this is L33, all are going to be ones, and you can see that the rest of the things are nothing but the matrix multiplication of these two matrices. So, you can see that these are the resultant. So, now in order to find this L as well as U, we are simply substituting it directly. So, that L11 becomes equal to what you say A11 and L21 equal to A22 and L31 is becoming equal to A31. So, similarly, by using these direct substitutions, we can find the values of L as well as U's. So, these are the various equations. So, you can see that by means of the direct substitutions, we can find all the unknowns like what you say U12, L22 and L32. So, once we have all these values, we can substitute that back into the original equation that gives you the lower and upper matrices. So, this is the continuation of that. So, these are the various formulas using which the rest of the elements are computed. So, let us take a small example. Let us try to see how this is actually implemented. So, now I am taking a matrix like this. So, my aim is very simple. I want to decompose this matrix into the matrix L as well as matrix U. So, now I am substituting all the values and I am going to find that. So, you can see that the first step is L11 equal to A11. So, L21 is equal to A21 and L31 equal to A31. So, now I can use the values straight away 3, 6, 1 and I can find the elements of this particular column. So, similarly, I can find the first row U12 and U13. So, from the previous equations you can find that U12 is going to be A12 by A11. So, it becomes 1 by 3 and U13 becomes A13 by A11 to get 1 by 3. So, this yields this matrix. Next, we have to find the second column. So, again you can see by substituting into the equations we are getting the value of 2 and 2 by 3 and continuing this to get the value of U23 we are getting this. So, this results in this particular matrix. So, once you have this matrix, fine, you can have the same logic to get your L as well as U. So, you can see that U is having ones in the diagonal and all the lower elements of U are going to be 0. So, you can easily check whether this is a correct decomposition or not by multiplying LU and it has to give the original matrix A back. So, you can check that for this problem if you multiply this we are getting our original back. So, this gives the verification procedure that crowd procedure is indeed right. Fine. Why should we do all the things? The reason is like this. As I said earlier, we are interested in finding the matrix inverse. So, the inverse matrix B of square matrix is defined like this, where if I multiply the matrix A and B, I should get what you say the identity matrix. So, this is what the definition of the inverse matrix. Inverses exist only for what you say singular matrix. So, if the matrix does not exist, it is called singular matrix, and matrix inverses are possible for non-singular matrices, and not all square matrices have matrix inverses. So, now the logic is very simple. I have the first column of B as 1 0 0, second column as 0 1 up to 0. These are the various columns of what you say the identity matrix, and I can use the Gaussian elimination to find the unknowns, and I can substitute that to get the inverse matrix. So, you can take one small numerical example to illustrate this. Let us assume that we are given a matrix 3 2 2 7. So, the objective is I have to find the inverse matrix for that. So, that means I have to find a matrix B such that if I multiply A B, I should get the identity matrix. So, since the matrix A is of order 2 by 2, the inverse matrix is also a 2 by 2 matrix, and it has to be something like what you say x 1 1, x 1 2, x 2 1 and x 2 2, such that if I multiply these two, I should get the identity matrix I. So, what is our objective now? Our objective now is I have to find x 1 1, x 1 2, x 2 1 and x 2 2. So, this is what I am going to do. So, I am going for augmentation. So, you can see exactly what is happening. To find the matrix inverse, I am going to augment the identity matrix. So, 1 0 0 1, which is going to be the identity matrix of order 2 comma 2. So, now I am going to apply the Gaussian eliminations. Probably you can recollect what is Gaussian elimination. So, now we are keeping 3 as the pivot element, and we are trying to eliminate this coefficient 2 by means of these transformations. You can see that this transformation is applied for this sort of the identity matrix also. So, when this transformation is applied for this, we are getting a value of 1 minus 2 by 3. So, like we discussed, by keeping this, we can find the value of x 1 1 and x 2 1. So, now you can see that the value of these elements are going to be what you say 7 by 17 and minus 2 by 17. So, now this represents the first column of the matrix inverse. So, similarly, we can find what you say the second column of the inverse matrix by substituting this to the second column of the identity matrix 0 and 1. So, now we can solve this for unknowns x 1 2 and y 2 2. Now, you can see that x 2 2 is going to be 3 by 17 and x 1 2 is going to be minus 2 by 17. So, now we know the value of x 1 1, x 1 2, x 2 1 and x 2 2. By substituting this into these equations, we are getting what you say the inverse matrix. So, 1 by 17 is common. So, I am getting a matrix like this. So, we can really check whether this procedure is right or not by multiplying this with our original matrix. You can see that by multiplying the original with the inverse, we are getting the identity matrix. In other words, by changing the columns of the identity matrix and by finding the unknowns, we can easily find the matrix inverse. The same logic can be extended for finding the determinant. So, you know very well finding determinant of the larger order is going to be a very difficult task. So, this is the determinant finding for a 2 by 2 and 3 by 3 matrices. So, the logic is very simple, apply, transform and conquer. So, decompose A to L and U. So, now the determinant finding of A is reduced to finding determinant of finding LU, which is nothing but the product of determinant of L and determinant of U. So, what is the beauty here? The beauty is very simple. The determinant of the matrix L is going to be 1. So, therefore, the problem of finding determinant is nothing but reduced to determinant of the matrix U, which is going to be the product of its diagonals. Okay. So, just by multiplying the diagonals we can find the determinant of the whole matrix A. These are some of the facts. If I have to exchange any rows or column, I have to multiply that by means of -1, and the determinant of matrix A and its transpose is going to be the same, and if any two rows and columns are same, determinant is going to be 0, and if any row is multiplied by a constant k, then determinant is also multiplied by the same constant. And similarly, you can see that the determinant is unaffected if any one row is altered by the elementary operation of another row or column. So, this is example. So, you have the matrix. So, I am applying LU decomposition, I am getting L as well as U. The determinant of L is going to be 1. So, the problem is reduced to finding determinant of U, which is nothing but the product of all the diagonal elements. So, the product of the diagonal elements is going to be what is say 3, 2 and 1. So, that means you can see that the determinant is going to be easy. Thus, we can come to a conclusion that how effective this strategy of transform and conquer. So, you can check this by finding the determinant in the conventional manner, and we can easily say that the results are matching. In summary, we can conclude that this is a very beautiful technique for solving number of problems, especially in matrix domains. For finding matrix inverse and matrix determinant, transform and conquer algorithms are very effective, and the Gaussian elimination and decomposition are very effective tools for finding matrix inverses and matrix determinants. Thank you very much. Next module we will discuss some more problems that are related to transform and conquer. Thank you.